So I was Kumun's lecture. You just gave a lecture before me, right?
Yes, we had that lecture on this recent paper on holographic application. This proved the existence of JKLT type.
Yeah, I see. Yeah, I think there's an interesting debate in the community going on about that paper. So it's quite, it's quite interesting.
Yeah, it's a very tough and a strong argument.
Mm-hmm.
There is no way to survive.
Mm-hmm.
Okay, I guess we can start. Hi, everyone. We are going to have the final lecture by Lars on new ideas in cosmology. Please, Lars.
Thank you very much. So today we'll have the last lecture. So it's been really nice to talking to you guys about some of the things that I find very interesting in trying to relate cosmology to Swampland. So today my plan of what I wanted to talk about is to give you some sort of idea of some of the new research directions that people have started to pursue, is sort of trying to address some of these issues associated to cosmology, and in particular to the sitter space. So some of these developments, they are not necessarily approaching this problem from sort of a swampland trajectory, but I think looking at sort of the things that we're seeing happening here, I think there are very close relations, and that is something that I would like to stress today. So to sort of recap what we saw yesterday, is we focused on the sitter space, and we sort of were interested in understanding the implications of some of the properties of the sitter space. In particular, the fact that that the sitter space seems to have a finite entropy because it has a cosmological horizon. And related to that, there are also thermal fluctuations because this horizon has also thermal properties. And what is meant is that it's very difficult to set up sort of an experiment in the sitter space where you can measure observables to arbitrary precision. In particular, what we saw is that if we're working in exact sitter space, this really precludes the existence of these asymptotic observables where you are allowing yourself to measure observables to an arbitrary high precision. In particular, what we saw is that at some point, if you're performing an experiment in the sitter space, then non-perturbative effects become important. So what you can imagine, for example, there are these thermal fluctuations. So if you have an experiment that lasts a sufficient long amount of time, then eventually these thermal fluctuations will nucleate the black hole and sort of destroy your spacetime for you. And in particular, what we saw is we reviewed an sort of older argument why, if you are looking at, if you're going beyond perturbation theory, if you're interested in also understanding some non-perturbative effects, then the de Sitter isometries, they cannot be realized in eternity. So if you sort of take t to infinity, then at some point what this argument suggested is that non-perturbative effects should sort of break the de Sitter isometries. And you can perhaps think about this as setting a finite lifetime on any sort of de Sitter-like universe. So this was just a very general argument, and it did not really tell us precisely what these non-perturbative effects are that break the de Sitter isometries. So today what we are going to do is we're going to focus on some new developments where you can probe some of these non-perturbative effects and the finiteness of the de Sitter entropy, sort of using techniques from quantum information theory. And in particular, what we're going to focus on is entanglement entropy. So before we can sort of study entanglement entropy in the Sitter space, let me make sure that everybody's sort of on the same page. So I'll give a brief review of some of the interesting features of entanglement entropy and how we define it. So the first thing that we can do is just sort of forget about gravity for a moment. And let's say that we're just either working in quantum mechanics or perhaps slightly more complicated if we're working in a quantum field theory. And let's say that we have some particular state psi. Then what we can do is we can associate a density matrix with a state psi, which is defined as follows. Sort of cat graph. So it's a matrix operator. So for example, what you can do if you're computing expectation values in this particular state, you can either sort of have an expectation value written in terms of this expectation value of psi, or you can write it in terms of the density matrix. So in particular, what you can have is something like this. Let's say that we're interested in the expectation value of some operator. You can equally describe this as a trace over the density matrix with this operator. So just sort of a useful way of defining your theory. Okay, so then let's say that we are having this particular density matrix rho. Then what we can write down is the so-called von Neumann or entanglement entropy, which is defined as follows. And we'll see in a moment why we'll typically refer to this as entanglement entropy. So here I put the Vn, which refers to von Neumann. So it's defined as the trace rho minus the trace rho log rho of this density matrix. This is sort of the definition. So if you have a complicated system, then this entanglement entropy can be very difficult to compute. And only in sort of particular situations, you can get exact expressions. It's difficult to compute, at least in general. Okay, so then some terminology. So if we are able to compute this von Neumann entropy, we can sort of characterize our state as either having vanishing von Neumann entropy or non-vanishing von Neumann entropy. So we typically say we have a pure state when the von Neumann entropy is 0. And we have a mixed state when the von Neumann entropy is non-zero. Okay, so typically what you can do, let's say that if you're starting from a pure state, then what you can do is you can try to look at subsystems and by tracing out sort of the region outside of the subsystem that you're interested in, and then compute the von Neumann entropy of that. So let me write it down. If we start from a pure state, we can typically obtain a mixed state. What I mean by typically will be clear in a moment. Tracing out degrees of freedom outside of the subsystem. Okay, so the picture that you can have in mind is the following. So let's say that I have some total system B, which consists of two parts, A, and its union with the complement of A, in such a way that we have a Hilbert space of the total system that factorizes. So pictorially, what you can imagine is that you have subsystem looks as follows. So here we have some subsystem A that can be embedded in a bigger system, which we call A complement. And then this total system would be B. Okay, so then let's assume that this total system B is in a pure state. So this is something that in principle you can always define. So if that's in a pure state, then we know if we write down the density matrix associated with this state B or with the system B and compute its von Neumann entropy, then that should be 0 by definition of a pure state. So we assume that our system is in a pure state. And what we can do is we can define this reduced density matrix as follows. We define the reduced density matrix of the subsystem A as a trace over the complementary region A bar over the total density matrix. And this object is typically referred to as the reduced density matrix. Okay, so what happens is if these regions A and A bar, if they are tangled, then what happens is that this von Neumann entropy associated with the reduced density matrix is non-zero. So then when we would compute S of A minus trace rho A, and this should be positive. So what it means is we can think of this von Neumann entropy sort of as a measure of the amount of entanglement between these two subsystems. And that's the reason why we typically also refer to it as entanglement entropy. So it gives you some sort of measure of sort of how much entanglement there is between these two regions, or sort of said differently, how much information you trace out when you are tracing over this complementary region. Okay, so this definition is sort of a little bit abstract. And as I said, it's difficult to compute these density matrices in general. But to give some intuition, I will present a very simple qubit example where we can see very explicitly how to compute these different quantities. Okay, so now what we will consider is we consider that there are two qubits, one of them in system A and one of them in system A bar. What we'll do is we'll make sure we prepare the system in such a way that these two qubits are entangled. So some notation, we can write down the state of these two qubits as follows. If you have write down vector ij, what we mean by that is state I in A and state J in A bar. Then the state that we will be interested in, or that we can write down, is the following entangled state. So normalization factor. And you might, when you look at this, you might recognize that this is an entangled state. So what happens, let's say that we are performing a measurement on one of the qubits, and then it will collapse to this superposition. The superposition will collapse. So then we'll precisely know what the state is of the other qubit. Okay, so let's say that we now write down the density matrix of the total system. So that was defined as follows. So using our expression in terms of the qubits, this takes the following form. So you see here we can do everything very explicit. Good. And now what you can do is you can look at this particular matrix. So you can, if you want, you can write down particular basis vectors for this. And then when you compute the von Neumann entropy associated to this, this is given by minus trace rho log rho. What happens is that this density matrix obeys some good properties that you can write this trace rho log rho as a sum over the eigenvalues of this matrix. And then what you will find if you look at this density matrix and compute its eigenvalues, there is just one eigenvalue that is equal to 1, which means log of 1 is equal to 0. So indeed, we find that it's correct that we started out with a pure state, because the von Neumann entropy or entanglement entropy of the total system vanishes. Okay, but now what we're interested in is also looking at this reduced density matrix. So now we're interested in tracing over this complementary region A bar. So in this case, what that means is we trace out one of these qubits. So the way this comes about is as follows. We need to do is we need to sandwich our state between the following. We sort of take the inner product of the second qubit in A bar. And then when you do this trace, what you find is the following. So now we're just left with only the qubit in A. And you might see that this is equal to just 1/2 times the 2x2 identity matrix. Okay, so now it's pretty easy to see what its eigenvalues are because we have a diagonal matrix, so they're just 1/2 and 1/2. So then when you compute now the entanglement or von Neumann entropy of this, just this reduced system A, and then what you find is that this is equal to log of 2. Okay, so this gives an interesting interpretation in terms of what this entanglement entropy is, because we typically think about the entropy as being proportional to the log of some number of microstates. So in this case, what we see is that because there's a log 2 appearing, is that this entanglement entropy, it gives the number of entangled qubits, which in this case was 2. So sort of in this sort of simple qubit picture, we can also think of this entanglement entropy as sort of giving the number of bits. And this is also sort of an interpretation that we want to sort of also apply to the Sitter space, which is of course a bit more complicated because then you're really working with a quantum field theory instead of just this simple quantum mechanical example. Before I continue, are there any questions about the entanglement entropy? Okay, so let me then go on to the Sitter space, where we basically will use sort of the same techniques, the same properties and quantities are appearing, but it will lead to a very interesting interpretation when we think about entanglement in the Sitter space. And this relates, I think, to a question that we discussed yesterday, how we should think about the Sitter entropy. Because we'll see that we can interpret it as an entanglement entropy. Okay, so then the first thing that we need to do if we want to specify entanglement entropy in the Sitter space is to have a particular state. And we already, so I think yesterday, that we typically were interested in states that preserve the de Sitter isometries, at least perturbatively. So then in the Sitter space, there is a very natural state that preserves these de Sitter isometries. which is known as the Bunch-Davy state. This is typically also the state that is used, for example, when you're performing inflationary computations. And sort of one of the motivations why this seems to be a natural state, well, it's preserved all the de Sitter isometries, but then also at short distances, it basically looks like the Minkowski vacuum, which sort of is consistent with our intuition that at sort of very short distances, we don't really know the de Sitter curvature. Things should basically look the same as in flat space. So we can denote this particular state by 0 dd for Bunch-Davies. And then the density matrix associated with this state is the following. Okay, so what I will not explicitly show, but I will just tell you, is that when you compute the von Neumann entropy associated to this Bunch-Davy state, is that the total entropy is equal to 0. Sort of, I guess, one way how you could view it is, well, let me not go into that. Let me just say, okay, so we know that this the von Neumann entropy of this Bunch-Davy state is 0. So it's in particular, it's a pure state. And now if we want to define some reduced density matrix, and what we need to have is some sort of natural separation into two subsystems. And because the de Sitter space has horizons, there's a very natural way of doing that. So let's look at the Penrose diagram of the de Sitter space. So we also saw this Penrose diagram yesterday. So in particular, what we also discussed yesterday is that there are two natural static patches that correspond to the region that is in causal contact with an observer that is either living at the North Pole or the South Pole. So here we draw the North Pole. Here we draw the South Pole. And in the picture where we took the time slice, the North Pole and the South Pole, those were the antipodal points on the sphere. So we see that here there are horizons, two horizons, that naturally give a separation of sort of two subsystems. In particular, it's natural to expect that when we take the Hilbert space of the total spacetime, that it naturally separates into these two North Pole and South Pole regions. And this is something that we'll assume is true. Okay, so now we sort of have this natural separation of these two static patches. And now you can ask the questions, are the static patches entangled? Okay, so when we think about this Bunch-Davy state, you can ask yourself about what the natural state is when we restrict to one static patch. And in particular, what we saw yesterday is that because the de Sitter space has thermodynamic properties, is when we think about one of the static patch regions. So here I just draw a cartoon. Let's say that we're having an observer that is sitting, let's say, at the South Pole here. And what that observer sees is that there's thermal radiation coming from the horizon and an observer can measure. So in particular, what it implies is when we look at the reduced density matrix restricted to the South Pole, where we trace out of the North Pole region, that this should take a thermal result. So it has some normalization factor C, and then it's e to the minus h divided by t, where this h here was the generator of time translations in the static patch. So we can think of it as a Hamiltonian in the static patch. And t is just the temperature of the de Sitter space. So you might recognize this as some sort of Boltzmann factor. So what this tells you is that this reduced density matrix is thermal. You can also really explicitly show this just by starting out with the definition of the Bunch-Davy state and explicitly performing this trace. and then you find the same result. Here we just sort of argued for it by consistency of this thermal picture. In particular, what that means is when we look at the von Neumann entropy associated with this thermal density matrix, that gives an entanglement entropy that is non-zero. And precisely when you do the computation, you find that the entanglement entropy associated with the south pole reduced density matrix that is precisely equal to the de Sitter entropy. Exclamation mark. Okay, so what does that mean? Well, it means that we can really think of the de Sitter entropy as e to the s de Sitter entangled qubits. So in this qubit picture. So in particular, when we look at sort of these thermal modes that are emitted by the horizon, one picture that you can have in mind is the following. Here again, draw the Penrose diagram. Then we can have a thermal mode that is entering one particular static patch. But what this entanglement entropy tells us is that for each of this particular thermal mode, there's sort of a partner mode of an entangled qubit that is located at the antipodal region. So there's entanglement across this horizon. And this is one interpretation that you can give to the de Sitter entropy as sort of a measure as to how many entangled qubits or thermal quanta there are in this spacetime. So this is also a sort of a different way of seeing that there should be a finite number of degrees of freedom that you should be able to access. So yesterday we already argued a bit for that, but just by saying that this entropy is given by the logarithm of some number of microstates. So whatever happens, you should better make sure that you can only access a finite number of degrees of freedom. And the same thing is true here, is that we should only be able to access at most s de Sitter number of states, or maybe e to the s. Okay, and what we'll see is that naively, it seems that in the Sitter space you can have set up a particular situation where naively you would be able to access more than s de Sitter or e to the s de Sitter amount of qubits or states, and there should be some sort of mechanism that is preventing us from doing this if we are supposed to take this de Sitter entropy seriously. So are there any questions about it?
Excuse me, may I ask?
Yeah, sure.
So I was just wondering if I don't know if you possibly will talk about this, but if you have consider this from other coordinates, I mean, like point coordinates, or I mean the other foliations of the Sitter space-time, can we find this finite entropy using those coordinates as well?
Yeah, so in principle, I mean, physics should be sort of coordinate independent indeed. So it's the most natural way of sort of phrasing the finiteness of the de Sitter entropy is given in these static coordinates, because that's the sort of, when you're working in these static coordinates, then you see that when you have an observer at the pole that sees a thermal spectrum of particles. So when you use Poincare coordinates, that is slightly less natural. But in principle, you should be able to phrase some of these ideas also from sort of a Poincare coordinates. And in particular, what you can, there's an argument indeed where, for example, you're looking at inflation. So what happens is that if we're working in the static patch, we can have these thermal modes that are being created. But let's say that we're working, as you suggest, for example, in Poincare coordinates, then we typically say that there's these modes that are being stretched over the horizon. So these two different pictures, modes being stretched over the horizon, or these thermal fluctuations in the static patch, those are basically the same physics. So there's always some sort of translation that you can do when working with different coordinate systems.
Yes, thank you. And you mentioned it's topological effects that make the entropy finite. I'm not sure what, I mean, yes, so these different, I mean, I didn't understand what's topological here, so.
Yeah, I'm not completely sure what you mean by topological. So, so what I said is that in perturbation theory, the entropy is infinite, because that's the limit where you take G over L to some power to 0. But then it's non-perturbative effects that should make it finite.
Yes, yes. I meant non-perturbative.
I see.
Sorry. Right.
Yeah, so maybe I think what we'll see today, so what I will do in a moment is we'll sort of consider a sort of a situation where naively it seems that you're able to access more than S the sitter amount of entropy. And then we'll see sort of what type of non-perturbative effects in that case can correct that result to result in a finite entropy.
Yes, thank you. Thank you.
Yeah, so that is just one example where we can sort of identify precisely what we mean by these non-perturbative effects. But in general, I think it's not completely clear what those effects should be.
In the sitter space, as you said already in the previous lectures, we are continuously generating modes and which are stretched beyond the horizon. So we expect that these entanglements somehow is time dependent, or it's not a constant, it's constantly evolving or constantly increasing somehow. So is that right? So how we can see this dynamics in terms of entanglement?
Yeah, that's a very good question. So I think if you're just looking at the Bunch-Davies state, then that is a time-independent situation. So in that case, there's not really a way in which you can say that there's sort of a time dependence to the entropy. So what I will do is I will try to set up a state where there's really an observer that is sort of collecting this radiation and then computing the entanglement entropy of that. And when you do that, you're moving away a bit from the Bunch-Davies state. And that will really lead to indeed a time-dependent situation. So another way of viewing is what people have also done is, for example, let's say that you're looking at the sitter space in sort of an inflationary setup, and you're imagining that you're like an observer sort of that is living in flat space after a period of inflation. And sort of the modes that you're measuring are sort of like modes that you can measure in the CMB. And there it indeed naively seems to be the case that if you are computing the entanglement entropy of that at some point you will exceed S the sitter. And then the question is, what are the corrections that come in that make sure that you're not exceeding that? And I think there's sort of an old perspective on that and a more new perspective. And I think we'll sort of talk about it both.
So if we start from zero entanglement at the onset of inflation and let it go, can we find some time scale beyond which we saturate this number that you mentioned here to the power S?
Yeah, exactly. Yeah, exactly. Maybe this is a nice bridge to what I wanted to say next. So let us try to consider precisely that situation and then see what happens. Okay, so the picture that I have in mind, or that we just talked about, is let's say indeed that you're considering some sort of inflationary period. So now what we're going to do is we're going to draw the Penrose diagram of the sitter. just imagine that this horizon is straight. I don't want to draw it again. And then we're sort of imagining, let's say that there's inflation ended at some point, and we're observers that are sort of living here. And in principle, what we can do is we can measure fluctuations of this early phase of the sitter expansion. So, for example, by doing measurements on the CMB. And so then what you can imagine, there are sort of modes that are being stretched over the horizon. and that are being collected by our observer there. And then typically what happens is that there's sort of one, let's call it a qubit. There's sort of one qubit or one mode that is being generated per e-volt of inflation.
Is it an assumption or?
It's not really an assumption. So because what happens is that the typical time scale indeed for such a mode to be created in the jitter is precisely given by the Hubble parameter. So it's, for example, similar for like a black hole that this is given by the Schwarzschild radius. So similarly here, this is given by the Hubble radius. And you can really make this precise by really computing the entanglement entropy. For example, so what we'll see is we'll go to a simplified example in 2 dimensions where you can make this extremely explicit, and then you can also see this happening. But then what happens if you are now, let's say that indeed each qubit information is sort of exactly terminal, it's independent. So then indeed, as Madi was saying, what would happen is that this entanglement entropy would grow if you're starting to collect more and more modes. So what it would mean is that there's a violation of the amount of entropy that you see. So the entropy that you're collecting, let's say, call it the radiation, it becomes bigger than the jitter entropy, precisely when the amount of e-volts that are elapsing are also bigger than the jitter entropy. And sort of naively, if you're just looking at inflation, you might wonder if there's anything that goes wrong by doing this experiment. So this is some sort of information paradox in the jitter space. So naively, you would be able to say there's nothing wrong with having a period of inflation that lasts longer than as the jitter e-volts. But by doing that, it seems that I would be able to have an information paradox in the sense that I can collect more entropy than should be possible given by the finiteness of the jitter entropy. And so this is sort of what I would call the old perspective on this problem. And there's a nice reference where they explain this problem and they sort of give an interpretation of it. So this reference from 2007, they basically suggested, okay, there's this problem there. So what should happen after as the jitter e-volts of inflation is that inflation should somehow stop. So they sort of just wanted to prevent this information paradox by at some point ending inflation. So this will put sort of a bound on the lifetime of the jitter space given by the jitter entropy, which is much smaller than the naive estimate of e to the as the jitter. But what has happened over the last 3 years, roughly speaking, so there has been a new perspective on this problem that arose originally from the black hole information paradox, but by now has also been applied in the jitter space, where they were able to identify precisely what happens when you sort of are crossing this threshold, and to see sort of that there are particular non-perturbative corrections that correct the entropy in such a way that you don't run into this paradox. Good. So I'll not be extremely explicit about precisely how you compute these non-perturbative corrections. So I would just sort of say in words what people have done, give you the reference, and then you can either look at it yourself, or later, if you have some questions, feel free to send me an email. So what has happened is that what has been realized over the last few years, and there's a nice reference on this. So it's a review article with the following archive number. Is that when you're computing the entropy in gravitational systems, then the sort of the von Neumann entropy formula that we used in order to also generate this, that you can use to generate this information paradox, it actually receives corrections. in particular. So when we think of a gravitational system, if we have want to compute the entropy of a subsystem, it receives corrections. And let me show you how those look like. So let's say that we have some subsystem R that is coupled to a gravitational system. So it can be a black hole, it can be like an inflationary type of setup. Then previously what we said is we're just interested in computing the von Neumann entropy. So but it turns out that this formula receives a correction, and that looks as follows. So there's sort of a Bekenstein-Hawking area type of term, where I will give you a picture of what I mean by this region R and the region I. So let's say that we want to compute the entropy of a subsystem coupled to a black hole. So then we can, so for simplicity, I will draw a black hole in ADS. There's a singularity here in that case. Now what you can have in mind is that we take this ADS space-time and we glue some flat region to it here, in which gravity is shut off. And that is a necessary condition in order to really make precise what we mean by sort of having this subsystem and this vectorization of the Hilbert space. So what happens is that we can have radiation that is coming from the black hole, which we decide to collect in some particular region R in the flat space region, or it's also typically referred to as the bad region. There's some region R. So you might naively say, okay, when I compute the entropy associated with this region R, I can just compute the von Neumann entropy of this region, but it turns out that this formula receives corrections, and you need to allow for the possibility of a so-called island region that lies in the bulk of the ADS space and ends at some endpoint I. So if you want to compute the entropy of this region R, what you need to do is you need to compute the von Neumann entropy of the union of this R region and this island region, and you need to include this area term that is associated with the island. Sort of the location of this island is precisely determined by extremizing this formula. So you're basically looking for the possibility of having an island by taking derivatives of this total entropy formula, solving for an extremum, and then that will give you the location of an island. Okay, so why do I say that this is a non-perturbative effect? Well, the way how this formula has been derived is a bit complicated, and I will not spend too much time on that. Sort of to give you a little bit of intuition. What happens is that in order to compute this entropy, we needed to specify this density matrix. In order to compute this density matrix, people typically make use of what is called as a replica trick. So instead of just computing the density matrix rho, you're imagining that you're sort of imagining a replicated manifold rho to the n. So you take n copies of your density matrix. That turns out to be an easier object to work with. And then in the end, you take the limit back to n going to 1 again. So typically what people have considered is when they're considered this density matrix rho on a particular manifold. So previously what people have just considered is sort of just taking n copies of this density matrix. But it turns out that if you're working in gravitational systems, because these replicated manifolds are typically connected by some particular branch cut, is you can have situations in gravity where there's a wormhole that is connecting these two different replicated copies. So these go hence by the name of replica wormholes. So those are quite complicated geometries to compute. But the upshot is if you, in the end you take the limit of n going to 1, you find precisely that you have this correction term to the entropy. So this is sort of a little bit of intuition where this formula comes from. And to see some bit more details, I would advise you to look at this reference, or if you're interested, we can discuss this also later, or you can send me an email. Okay, so sort of let's say that we just sort of accept that this formula is there. It arises from these non-perturbative wormhole effects. Then this island formula is telling us that what we should do is we should extremize over this island. in order to find its location. And let's say that there are multiple possible extrema, then this recipe instructs us to take the one with the lowest entropy. Okay, so this is sort of the general recipe. And you can, for example, the picture that I drew here, people have initially used this island formula to compute the entropy of, for example, black holes. And then you see a similar situation that naively, if you would just sort of use the just the von Neumann entropy, it seems that the radiation entropy just keeps growing in violation of the entropy of the black hole, which is finite. But then when you're using this island formula, you find that these corrections at some point kick in. And that's when you will have an entropy that either saturates if you're looking sort of at a eternal black hole, or goes down when you're really looking at an evaporating black hole. So this general recipe is very interesting, but in order to really do explicit computations, it's typically difficult in generic situations. So then we have to go to sort of a simplified setting. So that's what we will now do by applying this island formula to a situation in the Sitter space. And in particular, we will be interested in looking at the Sitter Jackie Teitelbaum gravity. Okay, so what is JT gravity? In general, JT gravity is a particular two-dimensional model of gravity coupled to a dilaton field. So in 2 dimensions, gravity is trivial. The Einstein tensor is identically 0. But if you're allowing for this coupling to a dilaton field, then you do have some dynamics. And what is interesting for us is that we can also obtain it really from a reduction of the 4-dimensional theory of gravity. In particular, if you're interested in JT gravity on the de Sitter background, we can obtain this from a reduction of a 4-dimensional black hole in de Sitter. In particular, we can obtain it as a reduction of a 4-dimensional Narii black hole, which is just a, you take a Schwarzschild black hole in the Sitter space and you take its radius as large as possible until the cosmological horizon and the black hole horizon are very close to each other. In that case, what happens is that the geometry is ds2 times s2. And then you can perform a reduction on the s2 to obtain a 2-dimensional model of gravity. So when you do that, you on the level of the action, you find the following result. So there is a particular constant term that is related to the de Sitter entropy. And then there is some dynamical piece. So we sort of have the generalization of an Einstein-Hilbert term, where we now have this coupling to a dynamical dilaton phi. And then we have a positive cosmological constant. And there are also in particular boundary terms that you can include and couplings with matter. Okay, so when you look at the equations of motion for this particular theory, find the following result. So there are 2 equations of motion, one of them associated with the metric and one of them with the dilaton. So sort of the metric equation of motion, which is sort of the generalization of the Einstein equation, is given by the following. And so this is the left-hand side, and then the right-hand side is proportional to possible matter couplings. So it contains the stress tensor. And then the equation of motion for the dilaton, that just sets the Ricci scalar to be a constant, so that imposes that you're working in the Sitter space. Okay, so let's say that we're now interested in studying matter coupled to this JT gravity model. So that will be useful because we're interested in sort of radiation that is being emitted by the horizon. So then we need to have some matter coupling. Then what we can do is we can couple to conformal matter, so that is conformally invariant. In particular, what we want to do is we want to impose that this conformal matter is in the Bunch-Davy state, because that's the state in which we have these thermal properties of the Sitter space. So then what we can do is useful to define the following coordinates. So these are sort of these coordinates sigma plus minus. Those are the analog of the Winkler coordinates in flat space. So they're given by the following relation. T is just the static time coordinate, and R star is this Tortoise coordinate, which can be defined in terms of the normal radial coordinate in the Sitter space as follows. Okay, so then imposing that we're working in the Bunch-Davy state, or just saying we're in the Bunch-Davy state and we compute the stress tensor, what you find is that the normal ordered stress tensor in the Bunch-Davy state, expressed in this in these light cone static coordinates, gives a thermal result, which is precisely what we were after. So here C is just the central charge of the CFT that we're working with, so of the conformal matter coupling, and beta is the inverse de Sitter temperature. So it's given by 2 pi L. Okay, so then when you take this particular thermal stress tensor, you plug that into the equations of motion, then you can find the following solution for the dilaton. So here phi 0 was this constant that was proportional to the de Sitter entropy. Here there is the Newton constant appearing. Finally, there's a term phi s is also a constant. And then we have that being proportional to the static radial coordinate. So in particular, we noticed that this is a solution for the dilaton that is time independent, which makes sense because the Bunch-Davy state itself is time independent. Okay, so when we now look at the Penrose diagram associated to this particular model, we get something that looks like the following. So the Penrose diagram looks slightly different than the one for high dimensional de Sitter space, in the sense that it's a rectangle and not a square. We still have our two static patches here, but what we now observe is that there are regions here, 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 and here, where the dilaton goes to minus infinity. And here the dilaton goes to infinity. The way we typically interpret this in JT gravity is, so the dilaton is related to the inverse gravitational coupling. So the regions where the dilaton goes to minus infinity are regions where gravity becomes very strong. And we typically interpret those as the remnants of the black hole singularity that we started out with. Because we started with this Nari black hole, we did this reduction to 2 dimensions. So now what we see here is we have a cosmological horizon. There's sort of an expanding region, but then there's also a black hole horizon. So this is typically what you find when you do this reduction from 4D to 2 dimensions. Okay, but what we're now interested in, so we now have this interesting model where we can compute everything exactly. But what we're interested in is trying to compute the entanglement entropy of radiation by using this so-called island formula. So in this particular Bunch-Davy state, there's not really when we look at it from a static patch perspective, there's not really time dependence. There's no way in which an observer can sort of collect radiation and compute the entropy of that. So what we need to do in order to have such a situation, we need to slightly modify this Bunch-Davy state by saying that, okay, in the Bunch-Davy state, you have radiation that is going, that is right moving, and there's radiation that is left moving. But what we now want to do is we want to imagine that we're just collecting radiation somewhere, so there's only radiation going in one direction. This is what we can do, is we can try to look for a new solution for the dilaton, which having a slightly different stress tensor. So now what we'll impose is that this component of the stress tensor is 0. And the other component still takes its thermal value. Oops, that should be thermal. So that should be pi c over 12 beta squared. So what this means is that the fact that we set this component of the stress tensor to 0 means that we shut off radiation along the sigma plus S constant slice. By shutting off, what we have in mind is that there's really this observer that is collecting radiation, and we will use that observer to compute the von Neumann entropy. In particular, what happens is when you now look for the new solution for the dilaton in this particular state, is you find that there's this correction term that appears. This correction term takes the following form. So there's still this R over L that is appearing, but now there's an additional logarithm that depends on X plus minus L. Where in this case, this X plus is related to the static time coordinates as follows. So in particular, what we now see happening here is that because there's this logarithmic term here, this now generates some time dependence. And when we express it in terms of the static time coordinate. So now what we can do is we can imagine the following situation. So we now have this new solution for the dilaton, and we can try to compute the entropy in the following way. Draw just the relevant part of the Penrose diagram. So here we have our static patch region. And now we're imagining that we have a radiation region where we're collecting the radiation here. And then this island formula tells us that we should allow for the possibility of having an island here. What is important that in this just given by the von Neumann entropy. So this would really be the thermal result that you initially expect. But then what happens is that in principle, there can also be a second non-trivial island, which I will call the horizon island, because it's very closely located to the horizon. So in terms of these the x coordinates, what happens is that this island is located at x minus roughly 0, which corresponds to this region here. And in terms of the x plus coordinates, it looks as follows. Okay, so then when you now plot the entropy associated with these two islands, you get the following picture, and then it will basically be done. So as a function of time, the entropy that we now get is the following. So there's the possible contribution of the trivial island. So remember that when we are applying the island formula, if there are multiple possible islands, we need to take the one that gives the lowest entropy. So initially you will have the trivial island that gives the dominant contribution. But then after a while, there's also this horizon island, which initially starts out at the Sitter entropy, but then goes down. So what happens is that this is the Sitter entropy, because what we need to do is we need to take the lowest possible value. The entropy will take the following curve. So initially it goes up until the horizon island takes over and gives the lowest entropy, and then we're going down. So what we see in this case, very importantly, what always happens is that the radiation entropy is smaller than the de Sitter entropy, sort of respecting the finiteness of the amount of states that we have at our availability in the Sitter space. So the conclusion in that case is that a potential info paradox is avoided. Precisely because we're allowing for these non-perturbative effects that gave rise to this island formula. And I should put an asterisk here, because what does happen is that because you're collecting lots of radiation into the Sitter space, back reaction at some point will become large. And it seems very likely that you will not survive this experiment. So I don't think I have time to discuss that in much detail. So if you're interested in that, I'll just give you the reference, and you can also send me an email later. Okay, so I'm quite out of time. So let me just conclude here with some general lessons about what we just saw about this JT gravity example. So in general, what we have learned is that quantum gravity tells us that when we're thinking about the Sitter space, that it should have a finite number of states. So we saw that in perturbation theory, so in the limit where G over L to some appropriate power goes to 0, the number of states goes to infinity, and there's not really a constraint. That makes sense because in that limit also the Sitter entropy goes to infinity. However, non-perturbative effects should be included in order to make the Sitter entropy finite. So in particular, what we should have is that non-perturbative corrections need to modify the physics in the Sitter space. In some sense, we can think of this as sort of a Swampland prediction. So the Swampland tells us, or quantum gravity tells us, that the Sitter entropy is finite. And this leads us to the conclusion that there are particular non-perturbative effects that we're typically not taking into account, but that are needed to be taken into account in order to have consistency with this finiteness of the entropy. So in particular, what we saw when we're computing the entanglement entropy, we have better control of what these non-perturbative effects are. And then indeed, we see how a potential information paradox can be avoided in the Sitter space. But then, of course, it's a very natural question, and something that is one that's very interesting to work on, is to try to understand sort of what are these non-perturbative corrections in different type of observables. So here we just looked at the entanglement entropy, where we could be a bit more precise about what we mean. But I think it's an open question if such effects also play a role for different observables, and that will be a very exciting prospect. So let me end on that note, as sort of a call to action, in the sense that I think it's a very important open problem that everybody should work on. Yeah, thank you very much. Sorry for going a bit over that.
Thank you very much, Lars, for this great lecture. So we have time for questions. Maybe I can have one question. So corrections that you said to the entropy of subsystem in a gravitational system is basically the very existence of the horizon, right?
Yeah,
which is kind of perturbative, I would say.
Yeah, it's a little bit subtle. So what I glossed over a bit is, so one of the reasons why people typically go to JT gravity, because in that case, you have these regions where the dilaton goes to infinity and gravity really decouples. And then you can sort of unambiguously say, okay, there's this subsystem and the Hilbert space is like this tensor product. So it turns out that sort of in a generic theory of gravity in higher dimensions, when you try to do something like that, there are no sort of asymptotic regions where gravity completely decouples. And I think it's also clear in general in quantum gravity that the Hilbert space does not exactly factorize. So in order to sort of make the story precise in higher dimensions, I think needs a little bit more work. And I think it's a fair point of you to take. This really only applies when you really can understand that you can really exactly factorize these Hilbert spaces, which in general seems to be quite difficult.
Very nice. So there is a request in the chat that
I can share the lecture notes, so that's fine. I can send them to Nadi.
Okay, good. Any other question?
Excuse me. So may not understand well, but isn't it the case that in the static patch, some of the symmetries of the two-state space are already broken? So that perturbative treatment that you mentioned yesterday might not work, or am I?
So what happens indeed, if we're looking at the isometries, then there are particular isometries that indeed do not preserve the static patch. So you can have isometries that if you're starting out in a static patch, they would sort of mix different static patches together. Of course, it doesn't necessarily directly mean that the de Sitter isometry is already broken. Sort of just by focusing on a particular static patch, you're sort of doing similarly like to a gauge fixing. But in general, the physics, if you're doing computations in the static patch, then that should still preserve the de Sitter isometries, even though that you're fixing a particular static patch.
Yes, thank you. Thank you.
Yeah, thanks for the question.
I also wonder if there is a connection between the time scale that the Transplanckian sensory conjecture introduces into the picture and this dynamical, I wouldn't say dynamical, this ever-generating mechanism for entangled entropy or general entropy. And if you have a better understanding in this two-dimensional gravitational picture.
Yeah, the time scale is slightly different, I think. So typically the time scale where you see this curve turning around, it's sort of like known as the page time, is typically given in terms of number of e-volts, is like of the order of constant times S de Sitter. Whereas this Transplanckian censorship conjecture is typically the time scale that is known as the scrambling time scale. It scales like logarithmically with the entropy. So it's a much smaller time scale. So I think these sort of replica wormholes and page curve type of developments, they seem to be pointing towards the fact that there should be physics at the page time that corrects sort of your standard results. And from this perspective, there's not a natural reason why the scrambling time or the TCC would become relevant. So that's something that would be interesting, I think, to understand a bit better.
All right, I see no more questions, and we thank you, Lars, for these great 4 lectures. I hope.
Yeah, thanks a lot for having me. It was great fun.
Okay, take care. Bye for now.
Bye.
Bye. And now we move on to the